Okay, we'll give people just a few more minutes to kind of come into the room, and then we'll get started for those who have just joined. Hey everybody, welcome to the workshop. We're going to be talking about StarkNet Account Abstraction and what's new. Um, Sorry I wasn't able to make it last time, mix up on my end, but for anyone that was here, is this about how many people joined last time, or should I give it a couple more minutes for people to come in? Looks like there's a decent amount of people, so we can just get started, and it sounds like it's being recorded, so we can share it out later. Cool. Are you guys able to see the StarkNet Account Abstractions presentation?
Yeah, we got you.
Okay, cool. So, StarkNet Account Abstraction. It's been a long time design paradigm in StarkNet. It's one of the things that we wanted to kind of come out with out of the gates to give developers some utility. A lot of people have taken this and run with it. Terrence is one of them on the call who's implemented some pretty interesting things. I'm going to go over what it is at a high level. We at StarkNet EDU, which is like the collective for the dev advocates for Starkware, have put together a tutorial. I'm going to walk through a little bit of how to do that tutorial, but also what's changed with the recent account abstraction and accounts on StarkNet changes. So, account abstraction, it's really just a really simple contract concept, and that's just that accounts on StarkNet are smart contracts. It's as simple as that. There are a few caveats prior to v0.10.0. So when I say things have changed in the architecture, I mean from prior to the release of v0.10.0 and then after v0.10.0. So the only difference to a regular smart contract on StarkNet and an account contract is the execute, the canonical execute entry point. That's now been updated to execute, validate, and validate declare. We'll go over what those are, what each of those entry points are, but this is what that used to look like in code. And you'll notice this is the old syntax. So along with some platform and architecture changes, the syntax of your Cairo contracts has also changed. So you'll see that this used to be, the simplest smart account abstraction smart contract. An account on StarkNet could have just been an execute entry point. And what do we want an account contract to do? We want it to execute another function on another contract for a known entity. So for typically a key pair, assigning key pair. So in this situation, there was no key pair. It's just, broken down to a hello world account contract. This contract simply executes contract code on another contract with line 14 where it says call contract. The only other caveat in the tooling and the tool chain is that when you're compiling a smart contract that is an account, you need to include this flag here for account contract. And that tells the compiler that it needs those extra entry points and to flag it as an account contract. Cool. And then while I'm going through this, we don't have a ton of people on, so feel free to reach out. Feel free to kind of interrupt me if you have any questions, and we can go over them.
Yeah.
Yeah, you have a question?
Hacker. Dear hackers, in about on time, reload on time, reload on time.
Is there anyone from Matchbox DAO that can
catch up of the workshop
that
from
can
yesterday, hosted of the Stark
all right, looks like I can mute him.
StarkNet account.
Okay. Did that screw with my screen share at all, or can you guys still see the screen?
No, it looks good. I muted him.
Okay, cool. Okay, cool. New syntax here. You'll notice that the curly brackets have been added to the end of the function calls. There's no more colon and end. Each of the lines, each of the expressions in the function bodies have a semicolon. So new syntax. And now we have the new entry points. So we have on, I didn't screenshot the lines, unfortunately, but hopefully you can see my clicker here. We got validate. So upon receiving a transaction, the account contract will first call validate. Like I mentioned, the whole point of an account abstraction and an accounts in general is that we want to execute arbitrary business logic on chain from a known entity. So validate will typically take the role of checking that the ECDSA signatures is correct. Those ECDSA signatures will typically be in the native curve, which is the Stark friendly curve. Head to our docs if you want some more information on that. It gets pretty into the weeds, but that's going to be the most optimized curve to sign with. And then Peterson hashing of the message digest. So this breaks that logic out into the validate function here. Validate declare. There's some talk about possibly separating validate declare and not having it as a mandatory entry point for account contracts. Follow closely with that and engage in the conversation on the forum. But yeah, right now validate declares transactions that require for declare transactions. So if you're declaring a contract class on StarkNet, that needs to be gated by some fee. Otherwise, we open ourselves up to a DOS attack or people basically running as many declare functions as they can for free and stalling the network. Execute. So executes essentially the same thing that we saw from the previous contract. The only thing is that in previous contracts, what you'll see a lot is that above this call contract here, you will see this execute also do the signing validation. So what we've done is we've split that up into two different entry points here. You'll still need the account contract flag. At its bare bones, those are the changes. So even though, account abstraction is this beautiful tool that we can do these crazy things with, at its bare bones, this is what the simplest account can look like on StarkNet. So one question is why? Why do this at all? One of the benefits of being a second mover in a smart contract accounts-based platform is that we can kind of see what the devs were looking for at other levels. So, devs on Ethereum have been clamoring for some version of account abstraction, and we've seen that manifest itself into EIP 2938 and EIP 4337. Even Vitalik has kind of thrown his hat in the ring. He says the fact that the Ethereum protocol itself requires everything to be packaged in a transaction originating from an ECDSA secured EOA makes account abstraction very difficult. So one of the things you guys get is being, Cairo devs and on this frontier, along with these syntax changes, you also get the beauty of, understanding what smart contract engineers have wanted for a long time from day one in account abstraction. Cool. So we've already seen some pretty awesome use cases. It really provides better UX. So you can have alternate signature algorithms. One thing that's really important about this is that we have a native signing curve, which is the Stark friendly curve and the Peterson hash. But that's very specific to StarkNet. If you're trying to abstract these concepts out, like Terrence did with the Face ID, you're going to need a different curve. There's going to be a different curve that exists in that secure enclave of some IoT device. Or you can even think of it as simply as, we are a layer 2 validity rollup that lives on top of layer 1. Well, it'd be good for us to be able to natively understand how to sign with Ethereum's curve, which is SEP 256K1. Upgradability. This is kind of a give and take here. EOAs are static entities on layer 1, which does provide kind of some good assurances. And here we can have wallets that are upgradable. Take that what you will. Social recovery, key management, Guardians. Argent's already implemented a really cool version of Guardians. This is going to be very important for the UX of crypto going forward. So, how if someone loses their key, how can they recover their wallet, their funds, their assets, their NFTs? Multi-sigs we'll look at a little bit today, and then paymasters. Paymasters is really a game changer because if you think that, one level of abstraction is that this known entity is running business logic on another smart contract, but then the next level of abstraction is who's paying for the transaction. Even though we want it to originate in this account, it could be paid for by, some other third-party entity. This opens the door for that. And really, all of this, okay, so standardization, with the leniency of account abstraction and the model of it, there's only really one or two rules, which is that it needs those canonical entry points. The community does need to coalesce around some grouping of rules, some subset of standardization that says, even though an account can be anything, by and large, what should operate on the network is this version of an account. And that's where Open Zeppelin comes in. Argent has some really strong primitives. The community has come together really well over that. And yeah, the whole point is basically devs are cool, devs do cool things, so run with it, do cool stuff on StarkNet. Okay, and so now we'll look at some code. Any questions to this point? Cool. So some of you might have seen this tutorial. It exists in StarkNet EDU. Are you still able to see my screen, and is the font size okay for everybody?
Looks good.
Okay, cool. Okay, so StarkNet EDU, this is where a lot of our tutorials live. You've probably seen StarkNet Cairo 101 goes over some of the basic concepts on StarkNet contracts, message bridging, debug. Feel free to kind of explore this space. There's a lot of good stuff in here. Capture the flag challenge, which is private. Whoops. But this one is specifically about accounts. And so I wrote this prior to the change, so we can really see the difference in the implementations from before v0.10.0 and after. There's go through the README if you want to know how to do the tutorial, but you should be able to go side by side with me if you're interested in doing it. I'll start from scratch. This goes over some of the similar concepts we went over in the slides. And this tutorial uses another couple community toolings. So we use StarkNet DevNet and StarkNet Pi as well. So I'll clone the repo here. Make sure that I don't have an old version. There's quite a bit of code to be written in this repo. There's quite a bit of code to be written in this repo. So there's two branches. There's an answers branch and a start here branch. So the start here branch of this repo has most of the answers and a lot of the code taken out. And so that's for you to kind of go through and, that's the workshop, that's the tutorial portion of it. If you do want some reference code, or if you do get stuck on this branch, you can always kind of go to the answers branch and those should all be operational examples. Okay, so we've cloned the repo. We start with answers as the default branch. We have a couple different pieces of tooling that we use. We will install those and I'll show you what they are. Okay, systems. I must have an older version of the DevNet. Okay, so like I said, we need to standardize around contracts. So Open Zeppelin Cairo contracts at the 0.4.0, the DevNet. If you're thinking about your dev cadence as you're building out smart contracts, I typically recommend starting with some type of unit test in the native testing framework, and then integration testing with the DevNet, and then move into the testnet. The testnet, it can be somewhat frustrating as a dev if you're just trying to, understand if your business logic and your integration is accurate, and you're not going to have to, debug something on mainnet. So I recommend using DevNet, and we use DevNet in this tutorial. So we'll start that. One more thing. So I have aliases for various Cairo environments. It might be helpful for you guys. It might not. I'll show you what it looks like. And feel free to hit me up in Discord if you want to look at this closer. But alias for Cairo dev, it just sets the most recent Python environment, virtual environment, sources it, sets some environment variables. So which network are we operating on? Which default wallet are we operating with? And then so if we wanted to use, and then so if we wanted to use, and then so if we wanted to use that, it's more and 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 maintenance for now. Reach out if you don't have it set up or you don't have it set up or you don't have it set up or you don't have it set up. Cairo dev will set up our 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 StarkNet DevNet. If you haven't messed with StarkNet DevNet yet, it's for short about how many of that's for short about DevNet yet, it's for short about how much it's an operate those in a way to certain accounts in a way to and we actually compare the evaluator the way that these tutorials operate is that we end up giving you some time for getting all of this information ready. So the validator checks the evaluator in a way that we expect, in a way that we if you want to read the evaluator, you want to read the evaluator sections, you can read test sections. So I'll show you where to start. I'll start with the hello contract. And that's in hello. You're going to get two pieces of information. Each of these exercises, you're going to get an Cairo program, Python scripts is a script to help you deploy the smart contract, and check your business logic, contract, so that we don't have to use the CLI for everything. This is the smart contract. So this is the smart contract. So this is validate, execute call. If you want to look at what the tutorial, I'll head over to the evaluator here, script for it, and validate. So the validate hello checker is checking that the caller address is not zero. Caller address is calling zero. Some contract with an address. That the TX info, the metadata of the transaction actually gives us an account contract. So the reason that the OS understands that this doesn't have an account contract address is because we provided file time an account file time. So this can give us an account contract address and then distinguish what on the platform is an account, what on the platform is an account. We're making sure that this specific contract is not signed. This is to show you that account abstraction doesn't only let you abstract signatures into various different sign-on schemes. You also can have a blank signature. You might need that for various different architectures. The various point is General Palpatine shooting the lightning, whatever works for you guys. Random is just something that was random in the evaluator. And then you get paid. You get paid. Absolutely worthless ERC20 is worthless. ERC20 is pretty awesome. So DevNet starts with an empty state. So we're going to deploy the evaluator to DevNet so that we have something to check against. And then we also need the ERC20 contract to pay you on DevNet. And there's one more piece of information which is not super pertinent to doing the tutorial, and that's the player's registry, and that's just to keep track of who on the chain has done and completed these exercises. So the way we deploy the evaluator here, CD into contracts, and again, it's all in the README, so you should be able to follow that. CD contracts. We'll break. I think I did not install my requirements. Nope. I'm not in the dev environment down here. We'll make sure these are installed here. There's just a couple other caveats to this tutorial. You get two other JSON files here. One is for config. This is just some tutorial specific configs. There's not much you need to do. The only specific thing you need to do is when you are operating this, you are on testnet, you'll need to put in an address, a public key, and a private key. You can get those from your Argent wallet. Let's make sure that I'm on testnet, so you guys don't steal my millions of dollars. Okay, testnet. So you just go into one of the accounts. Here's your address. For this field. You can export your private key. And again, this is all on testnet, but obviously you would not want to export your private key, and especially not screen share it to tens of people if you are on mainnet. So yeah, copy that, paste it here, and if you did want, you will need to grab the signing key as well. You can head over and read the contract for get signer here, and paste that in public. Great. So some tutorial specific configs, and then here's the account.json. So developing smart contracts can be a pain, especially when we are integration testing, because you want to check that some business logic had been carried out appropriately. And when you're testing it, there might be something that fails, but it could be in the layout of your call data and not necessarily the way that the smart contract was written. So this is a contract cache, and it basically serves as if the business logic of your smart contract looks good, but you're not calling it correctly, you don't want to redeploy that smart contract. So anything you deploy on DevNet will get lodged here in the cache, including the evaluator. Always in the wrong directory. All right, so while this is deploying, it's going to deploy the evaluator, the player's registry, and the ERC20 token. Just know that you have to do that every time you restart StarkNet DevNet. So let's say you leave your machine and restart it the next day. StarkNet DevNet is going to start with, again, a clean slate. You'll need to deploy the evaluator again. But while it's up, you can kind of just play with it. You'll see that populate here. While that's deploying, we can look at the evaluator.py just to see what what we're using StarkNet Py for. StarkNet Py gives us a client, which is just an interface to the chain, an account contract, so that we can pay for deployment fees. And then we compile these contracts that live here and deploy them. You won't need to touch anything in tutorial. It should be all laid out for you. So registry, while that's being deployed, any questions on account abstraction or the way this is laid out? Cool. You can kind of see the benefit of using DevNet here. You know, if I'm deploying these contracts on, these are all actually waiting for transactions to be complete. You see the await here. You know, if you're gonna wait for a transaction to actually be accepted on L2 on testnet, you know, you're probably gonna be waiting some time. Okay, awesome. Let's check our accounts.json. Yep, we have 3 contracts deployed: evaluator, player registry, and the ERC20. And now we'll go ahead with the rest of the tutorial. So on Hello Cairo, there's nothing to do. Anything that needs to be done by the operator of the tutorial will be denoted in action item, all caps. And you know, that'll be code that you need to write, or interaction code that you'll need to write in the Python script. So we'll just show you what, since there's nothing to be done for hello world. Can just interact with it. Let's check out the Python script we just launched. It's going to tell you what's it expecting. It's going to deploy the contract with the hello world template, get a client, fund the account. So, you know, anytime we're interacting on chain, we're going to need to pay for that invocation transaction. So we actually fund the hello world account that we just deployed with a little bit of way so that we can interact. We get the random value from the evaluator contract, and then we call the validate hello selector on the evaluator so that we can get paid. Here is another change that you'll see post v0.10.0. We have this new transaction version, which is transaction version 1. If something does come with a transaction version 1, I'll show you what the previous transaction version looked like. This is the old version of the tutorial, by the way. So this was transaction version 0. Version data, just trust me, this one's 0. Here's the difference in transaction versions. So from 55 to 62, you only need call data, signature, max fee, version 1. This is a protocol level nonce. So nonces were used to be held in the account data, account storage. I'm sure you all, you know, understand a nonce, but you know, we basically don't want there to be any opportunity to replay this transaction, and a nonce guarantees the uniqueness of the transaction for the account. Now after version 1, the account doesn't need to worry about it. Let me see if I remember which part of the tutorial we implement it, but I'll show you what it looked like. Okay, get nonce. So there was a storage variable that the nonce was retrieved and checked against. This is unfortunately the branch that you need to write the code, so I don't have the reference code to show you. But yeah, the nonce is all handled in the account contract, and one of the nice things about this new version is that the account contract can have, you know, in the Cairo code can have no understanding of the nonce and still guarantee transaction uniqueness. Okay. The other difference here is you'll notice no nonce. Nonce, it would be passed in additional data or call data and handled within the contract. The other difference here is entry point. So there's no entry point selector. That's all passed in the call data here. Get selector from name, validate hello. Awesome. Let's double check our account cache. We did deploy a hello JSON here, and it looks like we received a payday. So we should have gotten paid from this transaction. I think I might be running out of time. How long are these workshops scheduled for?
I've got an hour. I mean, you can go kind of as long as you need. There's another workshop at the top of the hour.
Okay, awesome. Then I'll keep going and then open it up to questions in just a little bit. So let's just make sure that we did in fact get paid. And you can see the StarkNet DevNet logs here, so we know that we are definitely interacting with DevNet. Okay, so let's double check that we got paid. This is something I use in my development flow. I would recommend you guys use it too. You know, the CLI is great for a lot of things, but when debugging and for kind of fast presentation of information, I find Postman is a really good tool. It does take some time to open. All right, while that's opening, we will show you signature. So we deployed a contract that had no concept of signature, no concept of ECDSA signing. You can see that on 57 here. Signature is an empty array. We're just going to make sure that we are indeed getting paid the money we're owed. This is a Postman collection that the EDU team has put together. If you are interested in using it, I find it helpful. Just ping me and I'll send you the link, or you can just type in StarkNet EDU into Postman, and you should be able to find it. Okay, so we're gonna call the contract on. This has a couple different environments for you to work in. Mainnet, this node is a JSON RPC node for when you're calling something like either Infura or Pathfinder or Juno. Mainnet, DevNet, and testnet. DevNet. Go to DevNet, localhost 5050. So let's check a couple things. We got output of this transaction hash. Let's get that transaction on DevNet. I have had the wrong port. No, 5050. Oh, put in too many hex prefixes. Okay, so accepted on L2. The way that DevNet operates is there's not an L1, so everything is going to be an L2 state. So accepted on L2 is great. We called it with this call data. If you want to try to debug, if there's something that doesn't look quite right, you can debug the call data there. Nonce is zero since the account contract is new, and some more transaction details. So how are we going to check that we did indeed get paid? And by the way, you might be asking who is getting paid in this situation. For operating on DevNet, we actually just use a pre-funded account. But when you do operate this on testnet, this will be the account that gets paid. So on DevNet, it's the actual first deployed account, which is this. And we're going to double check that this guy is getting paid for good answers. So call contract. This is another little trick that the APIs require certain formatting for various different fields. This needs to be not hexadecimal, it needs to be a felt representation. And this is just a little tool to convert. So I'll convert that hex to felt and put it in the call data. We're gonna call in our accounts contract cache here, we're gonna call it ERC20, rewards ERC20. And the entry point selector that we're gonna call on that contract is the balance of entry point. And this one actually needs to be hex. Okay. Sweet. So UINT 256s are broken up into low and highs. That's out of the scope for this conversation, but if you do have any questions on that, I can fill you in. Awesome. We got paid 118 decimal points for interacting with this this contract. Any questions about the flow of the tutorial there, and how to get paid and how to operate? Okay. Then we'll move on. So signature, we showed that signatures can be 0, but that's not what you typically want from an account contract. You want some signing scheme, some ECDSA signing scheme. This tutorial is showing you that you can pass that signature in call data. We're actually going to go to something that's slightly more descriptive, and that's this. Okay, so we have a public key. That public key is stored in the storage of that contract. So we have a storage var, and we have a public key. That public key is going to be the signing public key entity of the key pair for the start curve. So that the one that we operate in this signature to is the native curve, the most optimized curve for StarkNet. Constructor, this is a call once function where we write to storage. So when we deploy this contract, we deploy the public key, which means that we have to generate the public private key pair before we deploy this contract. Is valid signature. So this is a helper function for checking the validity of the signature. And as you've probably guessed, in validate, that's where we run this code. So in validate, we get the transaction info, and we make sure that the transaction metadata and signature is indeed valid. TX info transaction hash. This is the Peterson hash of the transaction contents. And when I say transaction contents, I mean that from 51 to 58 here, that is a Peterson hash of all of those values. Was there a question? Okay. Cool. So, our first look at signing. We do it in validate. Validate is called even when execute is called. So every transaction is going to be validated, but it lets us separate this execute transaction into what the execute transaction should do, which is it should execute arbitrary logic on some other contract. We don't have to mix up. We can kind of separate our concerns here. There's also a view function here for if you want to get the public key and if you want to know if a signature is valid for this specific public key. So if you think about, we saw what the simplest account abstraction was. This is the simplest account abstraction with the concept of a signature. Here's our Python script. We need to implement an account contract interface with this signature. We've done that. Private key is in our config.json, and here's how we generate the start key. This is the key pair, the public and private key pair coordinates for the signing key. ECDSA signatures, for the most part, it's going to be out of scope for this workshop. Elliptic curve signing is really interesting. It's super cool. It's something to be aware of, and it's a whole study of cryptography. But for the most part, the really important things to understand are that a private key can never be derived by its public keys, and we use this to illustrate ownership in kind of the digital world today. So when we have a private key off chain, you guys are all aware of this. I won't rehash it for you. Cool. We deploy the signature with the start key. That's the public key. We fund that account so that we can operate an invocation transaction. And then we format the call data here to call validate signature 2. And this is the account that gets paid. So what is validate signature 2 expecting? Let's head over to the evaluator and check. Okay, so validate signature 2 is now expecting that the signature of the transaction is not 0, and it is explicitly 2. We're also checking that it is an account contract. We went over that. We have an interface here for getting the public key. So I'll get the public key from your contract, and I'll make sure that that public key has a valid signature with the native curve. If it is valid, and the nonce is more than one. So here's kind of the trick of the tutorial here, is that you need to have had 2 valid signatures for the contract in order to get paid. If you don't have 2 valid signatures and you've only tried once, you're not going to get paid. So there's some of these little hiccups, these little gimmicks within the tutorial that you need to figure out, and you guys are getting the answers rubric here. But this is important in terms of what's changed in account contracts, because txinfo.nonce is new. The only transaction type that has a txinfo.nonce is a transaction type of 1, which is post 0.10.0. Let's double check the Python script here. Okay, and indeed we launched 2 invocation transactions so that we can bump the nonce. Invocation transaction hash, sign that transaction. Here's where we sign. Here's where we sign the transaction, and we include the signature in the payload. And we do that twice. So let's give it a shot. Python 3 signature 2.py. All right, it's going to tell you what you are expected to do. Sign the call data expected by the validator, invoke the validator, check with the signature, and call until you hit pay dirt. Okay, so we have 1 account deployed. That's going to be this signature 2.cairo, which means as far as our Python execution, we've gotten to here. Cool. Now we've gotten to here. No payday. So on the first one, since the transaction nonce was not 0, we did not hit pay dirt. Let's verify that. Double OXs. All right, so this is the first transaction we published, block number 11 on DevNet, accepted on L2, 0x0. So the nonce of the first transaction was 0, and we didn't hit an assert failure in the evaluator contract, but we didn't get paid. So this block was never executed. And then in the second transaction, nice. Okay, nonce is 1. We step into that function body in evaluator, and we emit the event for payday and get our award. So we should see our balance in the ERC20 contract here increase by 200, I believe. Okay, cool. 300, 18 zeros. Awesome. That is how we sign things with the native curve. If you were here at the beginning of this, when we went over the presentation, we talked about how the base layer Ethereum has different signing scheme. In that signing scheme is the curve pair for SECP 256K1. What we've done is, for a long time, we let you implement that. We provided some examples of that curve, and then people implemented it. I think Terrence dropped, but Terrence has an implementation of it in his code base. But now it's actually in the standard library. So now it's much easier to check Ethereum signatures. If you wanted to see, this is that library in Cairo Common from Starkware, Cairo SECP. So now it's optimized, easier to use. Everything's a little nicer, and it gives us access to the Ethereum curve. That's going to be in this signature 3. So in signature 3, this is an account contract where we store an Ethereum address in the constructor. And when we check, you'll notice that this signature validation check is much longer than our regular check. Now, not only is it much longer in lines of code, but it is actually more compute heavy as well. So something to know is that it's going to take more steps to verify an Ethereum curve than it is going to be to verify the StarkNet curve. So verify ETH signature UNT 256 here. Everything else should look fairly familiar. The rest of the layout is the same. Validate just calls that helper function. And then execute does its job to execute logic. So then the meat of this is here. How do we generate Ethereum private keys for that curve? There's a Python library for it. You can do it in many different ways. You could even just go into MetaMask and deploy a new account and export the private key. It's all going to be for the same curve. And then still need to fund the account with Way. Here's how we sign a message in the Python Ethereum keys library. And we are signing the invocation transaction on StarkNet. So everything is StarkNet specific, but we're signing it with a set of Ethereum keys. And again, we're dealing with version 1. So signature is added in the signature field, and nonce is included in the invocation transaction. Let's check that out, and then I think I'll close it after this one. Okay, again, it's going to give you a prompt here. So sign the call data using SECP 256K1 and invoke the validator check. We can go over and check the evaluator. A bit simpler here. This one is strictly checking that you've used the correct curve, which is the ETH signature. That's going to look a lot like the function in their function body. Okay, successful deployment. Signature 3 has been deployed here. And this all will take a bit more time. The Ethereum signing curve is just a little bit more compute heavy. We've deployed the account. We've most likely funded it. And we are probably here. You can put in some debugging statements if you do want to follow the execution of it. So you could say, mission complete. You can mess around with this really however you want. Something happened with our DevNet. This has happened to me with DevNet before worker timeout. Unfortunately, I think there might be a bug with how often you need to interact with it. So let's quickly start DevNet back up, redeploy our evaluator. Okay, while we're doing this and waiting for these to go through, 850. Any questions at all on the presentation for account abstraction in general, or the changes, or this tutorial? Nothing. Okay. Is this tutorial, has anyone been coding with me by any chance? Well, if you're watching this as a recording, I hope feel free to reach out to me with any questions. All right, the last one to deploy is the evaluator, which should go out soon. One thing to note there is in the utils, if you restart the DevNet, the tutorial will pick up that there's a restart, so you don't need to manually delete all of those contracts that we cached here. It'll understand that there's a new state, and it'll redeploy all of these contracts. Should be one more contract. There it is. Okay, signature 3. And one last time, we'll go through what that is doing. We are generating a Ethereum public-private key pair. This is for this specific curve, which is SCP-256K1. Distinguished because it's not the native curve, and it is more expensive to use. We're getting a client, which is just an interface that we can interface with the blockchain in Python with. We're deploying and compiling our signature 3.cairo contract here. We're funding it. Anytime you need to have an invocation on chain, you need to pay for it. So we need to have some way in this signature 3.cairo contract. This is to get us an interface to the evaluator so we can test our code. I have not touched on this yet. So here we actually need to get the nonce that is attributed to each account contract. Even though the protocol handles the nonce and we don't need to check that signing in the contract, we do need to include it when we sign. So this is getting that nonce so that we can include it in our signature. Format the TX hash, which in this case will actually be SHA-256, as opposed to the Peterson that we normally use. Sign that message hash, format it, and send it. It's all broken. Okay, we're running out of time, but this is kind of interesting. So the actual fee exceeded the max fee. So because that curve has more steps to validate the signature, we pay for that. We pay for the steps that are run in the contract, so that we actually didn't fund the account with enough money to pay for the validation. Unfortunately, I'm not going to fix this right now just because we're running out of time, but we just need to give a higher max fee. So this max fee needs to be at least higher than the steps to compute. All right, guys, I hope you enjoyed this. I hope it was helpful. If there's any last second questions, feel free to ask them. If not, ping me offline. And I've had a good time, and thanks for joining.
Thanks so much for taking the time and making it work. I appreciate it.
problem.